Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is Steve Dill. He is a chief architect in the cybersecurity solutions area at Lockheed Martin in one of their four major divisions called IS&GS, or Information Systems and Global Services. He's going to be talking today about system engineering. His title is Lifecycle Engineering and Cybersecurity. Steve.
Thank you. In the interest of disclosure, I came prepared for a 90-minute talk. So if you have, I was going to interrupt your plans for dinner, but Randy said that I shouldn't do that. So Lockheed Martin is a fairly large organization made up of a number of business areas, and one of them being Information Systems and Global Services. And we in IS&GS view system engineering as one of our core competencies. And so it's kind of a concept that is not well known or well followed among a lot of organizations, especially those who don't deal a lot with the federal government. So I wanted to bring that system engineering perspective to you today. Today we'll provide an overview of how INFOSEC or cybersecurity or information security, or however it's known to you, how engineering requirements and methods fit into an overall systems engineering process. So we're looking at the life cycle of a system. So you can consider information security as a discipline within system engineering, or you can consider system engineering as a discipline that contains elements of system security engineering. But anyway, today we're going to show you some roles of the engineer in the system security lifecycle, in the system engineering lifecycle, and then also some of the processes that are involved. So what is systems engineering? Systems engineering focuses on methods of problem solving and not the solution. So it's the journey that's interesting in system engineering, not the end of the journey. And so we view, if you make the journey complete, or well, complete's a good word for it, by focusing on the journey, you get to a more effective solution in the end, at the end of the journey. So it places an explicit and high priority on things other than the technology. So things like the economics of the solution, the cost, the performance, the safety, a number of other issues that are in totality become the system engineering priority. So we believe that this leads to a more effective solution, and there's a definition of it there from the University of Maryland's School of Engineering, if you want to see the competitor's point of view. So let's consider what is an IT system. It's hardware, software, so on, all these things that show up here. The hardware and software is probably the easy part. The hard part comes in how you handle the data, how people interact with the system, use the system, and get results from the system. The interfaces between your system and somebody else's system. The interfaces between people in the system. We can extend systems engineering to include multiple systems in the goal, so we can have a hierarchy of subsystems as an instance. One of the things we have to consider in this is then the business objectives. So some organizations measure the maturity of systems engineering within target companies. So in in the instance of Lockheed Martin, we are certified at the capability maturity model of 5 for some aspects of our systems engineering, or for almost all aspects of our systems engineering, and our software engineering, and our human engineering, and our resources. So that's a goal for us, is to be at CMMI level 5. Some organizations don't need to, or don't feel they need to get that well mature, or that well defined in system engineering. So you start out with not considering it at all. If you decide then that you need to do it, you can perform it informally. You can plan and track how you improve your systems, or how you operate your systems, how you design them. You can go to well-defined and then quantitatively controlled, continuously improving. Of course, the goal, we believe, should be continuously improving, but not everybody wants to spend that amount of time and effort on their processes. This kind of thing is gone now from the System Engineering Institute at Carnegie Mellon. It's become part of the NSA, and rates their suppliers, their vendors on a scale very similar to this. You started to see this kind of scale in the ISO processes, 27001. So this is kind of the heart of the way we view the system engineering life cycle in Lockheed Martin, and this is a very simplified view of it. So the block diagram in the middle, the wiring diagram in the middle, is a simple representation of a system engineering life cycle. In reality, you go through many of these in any kind of design process leading to a solution. So you can have this as a waterfall, or you can have it as a spiral development, depending upon what your courses are. But anyway, out of all this, the system engineering life cycle has a number of processes. Some of these are program control processes, some of them engineering, some of them support and organizational. So what might you expect in program control processes? And I'm inviting you to respond. Okay, so cost accounting is one of the program control processes that we might encounter. The program risk management as opposed to the technology risk management. Monitoring of engineering and subcontractor and material suppliers. In the support and organizational processes, we include things like the specialty engineering, human-computer interface engineering, safety engineering, performance engineering. These are all subsets that we view in the engineering pantheon of skills, and we view a lot of these as specialty engineering. And then, of course, the engineering processes. Now we're talking about things like the systems requirements phases, design phase, implementation test phase, and a support phase. And within these phases, we have the period of time when we spend analyzing what the mission of the system is intended to do. And from that, we try to gather high-level requirements. The system requirements can then find themselves as part of a system architecture. And system architecture is usually starts out as a very high-level architecture. It's designed to impart a concept of the system to the viewer of the architecture, to the reader, both to the design people and to the users. So out of that comes things like ConOps, the concept of operations. That breaks down, once you have that level, into you can start devolving your hardware requirements and your software requirements. Once you have the requirements, you can start doing a design. You usually at all the boundaries you see here, there's some kind of a review. You get into then implementation and test, where you actually design the system, you test it, both informally and formally. doing things like code and unit test, which is where you're testing small software modules. You test the hardware, make sure it meets its requirements. And then you transition the system to the real job, to the customer. So you have the deployment of it. You have how the operator operates it, how you're going to support it in the long run, and then in the end, how you get rid of it. And so if you've been thinking about this at all, you realize that all the way through here, there's a lot of roles for a system security engineer or an information security engineer in here. So they have roles to play in the program control processes, roles to play in the development or engineering, and roles in the support. You also have folks who have an interest in this from the customer side who are going to be paying attention to your life cycle. People like the chief information officer, the contracting officer. If you're dealing with a government, contracting officer's technical representative, who's the person that the systems engineers probably most have contact with. You've got information security program managers on the customer side, the security officers, the acquisition officers, in some cases privacy officers, and so on and so forth. So you deal a lot with those in the program control phase, where you're doing risk management, configuration management, material acquisition, engineering development, and task planning, engineering review boards, quality engineering, continuous process improvement, going back to the maturity model. Covered the I want to cover a little bit more on the supporting processes, because a lot of times we don't consider all the things that go into supporting a program. And some of you, if you're from within the CERIAS, probably are coming from other disciplines, and so this may make some sense. Things like integrated logistics support, user engineering. If you're in the management side of things, you're interested in size, cost, and schedule of the program. If you're a security guy, you're particularly interested in the vulnerability assessments, risk assessments from a technology point of view, but you may also be interested in requirements and verification, traceability, which is another one of the processes that we have to go through. And then we've got things like reuse and database engineering. And let's not forget training. So if I take the information security viewpoint of the systems engineering life cycle, I move boxes around. I can take a somewhat linear viewpoint of it. If we start from the left and work our way to the right, as in the other slide, you'll see some things that fall out at the beginning, some items that go across the whole time frame of a program and its deployment. The bane of nearly every systems engineer's existence is documentation. And you will find documentation requirements throughout. There's no getting away from it. So in this model that we've taken on here, we've been working with this model for quite some time. And not too long ago, NIST came out with their model of the system security life cycle, and it maps very well to this one, so at least we got validated. So we use this kind of a process to address all the security objectives that we find in the beginning of the process. We find that a lot of things that would normally think about as being end game issues, we need to think about very early on. One of those is the certification and accreditation activity. If you're working for a contractor who's working for the government, or you're working for a government, and not even ours, but any government, they want to certify and accredit that the system is operating in accordance with their requirements and their best practices. So if you wait to the very end to find out what those are, it becomes quite expensive in time and effort to go back in and fix things that you should have known about at the beginning. And so if you engage your certification activity, accreditation activity people early on, you have a better design in the end. So I think I'll just move on from here. So some of the activities that span the life cycle, and most of these are documents, are the information security plan, the policy specifications. Some of the activities that go on are things like the threat and vulnerability analysis. You first do this on paper, and then you may be able to have introduce some tools into the system to do this once you've got some software developed and some hardware designated. Disaster recovery is something that you want to think about early. You want to be able to plan in your system design for disaster recovery or business continuity or continuity of operations, however they talk about it. And then again, as I said earlier, think early on how you're going to dispose of it and how it's going to be operated. So I'm going to go through this system engineering life cycle and talk about break it down into the phases that we saw in the earlier one. So we're going to look at the systems requirement phase here first. So the goal here is to understand the organizational or mission needs. So as a security engineer, software engineer, or a systems engineer, you're going to be working with your customer to determine what their security requirements are in the system. And they're going to do a lot of hand waving. And they're going to say, well, it's got to be secure. And it's got to work. Can't cost a whole lot. And they'll go on and do things like this. So you've got to understand how you actually go to them, talk with them, and find out what their real requirements are. Now, they may write them down. Hopefully they do. They will have given a considerable amount of thought. But as you're reading it, you're going to realize that there's first level requirements, and then there's a bunch of requirements that make up that requirement. And so those are second level requirements. You may have third level, tertiary level requirements. All these need to be documented, verified, discussed with the customer, proven out, and then become part of the design. So that's the system requirements analysis phase of it, and the organizational mission needs are what drive those things. So you may eventually in your career, you will become involved in helping the customer understand what it is he really wants to do. At this time, you are also going to help them define what the certification criteria are. If you're doing this with commercial industries or hospitals or the energy industry, they all have guidelines that they have to follow. And if they don't already, they soon will have certification criteria that they have to follow as well before they can bring a system online. For the healthcare industry, it's based largely on privacy, patient information privacy. So at this point in here, in your life cycle, you're going to start defining what the system functionality is going to be. Again, you go back to the customer, you get from him his objectives, you get from him the environment in which the system is going to work. Is it going to be a shipboard system? Is it going to operate in a system operations center for a utility? Is it going to be the dispatch system for a trucking company? These all have, or freight forwarding, like an ILS type of organization, or the railroad industry where they're bringing goods in from Mexico and carrying them all the way up to the Great Lakes area. The interface analysis occurs in this phase between systems and within the system itself, and generally this phase concludes with a preliminary design review, and this is the customer's chance to feedback to you whether you hit the mark. One of the documents that you have to come up with in this time frame is the system engineering plan, particularly if you're dealing with the DoD or the intelligence community in any the Defense Department or the intelligence community in almost any of the governments. I've seen this in France, I've seen this in the UK as well as the United States, that they want to understand what your plan is for security engineering throughout, and it contains things like processes. So if you've got a set of processes, you tailor them to meet the plan. If your customer has a set of processes, you may have to tailor those to meet your objectives and your system functionality. You're going to work with the customer to establish milestones and a schedule, define the certification criteria within the plan, the roles and responsibilities for the customer in his operations mode will get defined in the security plan, because you have to design towards those kinds of goals. Also in the plan, you'll address the interconnection information sharing criteria. Information sharing is particularly important in government kinds of situations, and banking and finance industry, and to some extent in the energy industry as well, where you've got roles that you've got information that you have to protect from wide dissemination. In healthcare, it's privacy information. In the energy, it's usage information, billing information. There's a couple of sources where you can start to find ideas of what goes into a security plan. The NIH is one, their Office of Information Technology, and also the NIST, the National Institute of Standards and Technology, has a lot of documentations. In their case, it's SP 800-64 is a good source for this. So it may be part of the security engineering plan, it may be a separate plan. You're going to have something called the Security Specification and Policy. So what are we trying to protect is what we're going to describe in this plan. And so we have assets. What makes up assets? You got something on your tip of your tongue.
Any hardware that you need to protect?
Right, hardware.
Information as well.
Yeah, that's a lot of times we don't always understand that that's part of what we have to protect is the data itself, or the information itself. Yes.
Intellectual property.
Very good. Intellectual property is can be a number of things. It can be the way the system itself is designed. It can be what the system is trying to protect. It can be your processes, your internal processes, your external processes, all make up intellectual property. So you've seen the confidentiality, integrity, availability, accountability triangles and quadrangles. And so you probably are fairly aware of what you're trying to do with that. But accountability is oftentimes not thought of at the beginning of a system. People will bring in the idea of how do I account for how it's used and how do I make people accountable for what they've done on the system. And they wait until the end, to the deployment, to figure this out. The earlier you do that, the better, and you should address that in your system specification and policy. And then your customer is going to have a number of defining documents that you have to consider. I think we covered that one. Where do the requirements come from? Well, they can come from information security policies. They can come from non-information security policies. A lot of security requirements are being levied by the SEC on the banking industry and finance industry. They may not look like information security requirements, but that's how you're going to deal with them. Privacy is very similar to information security, and you're trying to protect certain information. You have to consider, or the environment, the threat environment that you're in is going to generate some security requirements as well. So if you're not connected to directly to the internet, you're running a control system, let's say, that's not connected to anything else, then your threat, you don't have much in the way of external threat if it's not connected. But you do have to consider the insider threat. And insider threat might be poorly trained operators. So you get some of your requirements from what happens when somebody fat fingers a command that they're trying to enter on the SCADA system and causes a circuit breaker in Colorado to trip that eventually brings the whole northwest quadrant of the United States into darkness. So those are the kinds of events that could drive security requirements. Mode of operations are things like are driven by the classification of the information that you're handling. Do I have to have my information compartmented, and do I have to show need to know in order to be able to access certain pieces of information on my system? I have to have security requirements that generate a design that allows me to have compartmented information on my network. Does everybody on the network have a need to know all the information that's on the network? Chances are the answer is no, and so you have to have some kind of requirements defined that allow you to design in the need to know information. In this phase of the system engineering lifecycle, you start to identify what your threat is and assess the vulnerability that you have to that threat and the vectors by which that threat may be realized. So who are your adversaries? What are their motivations? What are their capabilities? And how are they going to get to you? If you've got a large wireless system, that has one set of vulnerabilities and provides one set of vectors. An entirely wired system, no wireless, has another set. Yeah. Now I can take the approach that I'm going to mitigate all possible vulnerabilities in my system before I let it operate. How long do you think it'll be before that system comes online if I have to mitigate all vulnerabilities? Yeah, you grin. That's the answer. It never will come online. So we take a risk management approach. We mitigate that which we can mitigate easily. We have to to assess things that the expense of how expensive it's going to be versus the actual cost of what the cost of the breach might be. So I don't want to spend $600,000 to fix a vulnerability that the worst case is might be $10,000 of damage. Where we draw the line is an important consideration. So in vulnerability assessment, we have to identify the components of our system and assess each of those, the paths that can result in the security breach. And at the end of it, we have to be able to present to the customer what his level of risk is now that we've mitigated all these vulnerabilities. So he has to specifically state that he is accepting the residual risk in the system before it can get the authority to operate. So if you're a system security engineer, you can see that a lot of your time is spent in the front end of a program. And most people find this probably the least interesting part. And the most interesting part is the design phase, which is, in my experience in designing systems, is the shortest period of time in the design, in the delivery of a system, is in the design phase. But I agree it's probably one of the more interesting pieces. My experience is as a system architect, and so I find myself in the front end and in the beginning of this phase, and then usually by the middle of this phase and the end of this phase, I'm off to another program. But as a software engineer or a hardware engineer, this is where you get to strut your stuff. Before, you were trying to figure out what it is you were going to do. Now that you've got the plan, you've got the preliminary design, and now it's time to finish that design and get to the critical design review, which is often the gate whereby we come out of the design phase and into the implementation phase. So we're going to start doing some software development here of modules. We're going to start performing the more interesting pieces of risk and vulnerability assessment. This is where we start using tools to scan things, where we start working with the vendors to understand what their vulnerabilities are. You're going to start making some trades here on what products to bring in if you're using what's called commercial off-the-shelf or COTS, or free and open source software, FOSS. If you end up working with government contractors, you'll hear those terms a lot. So the security architecture for a system presents a lot of different kinds of views of what the system is going to look like. So you're going to have an overview of the entire system that's going to give a pretty picture for the customer. He's going to be able to look at it and goes, I understand what it is that I've asked for, and I understand how we're going to get there at a very high level. And then I start having other views that derive from that, the network security view. So I may have an architecture view of a bunch of boxes on a page that is my network for this particular system, and then I've got a security view of that network. I've got another one for the operating systems, perhaps one for the applications, one for the database. I may have data flow diagrams as part of my architecture, and that's one of the views that becomes very important in the implementation phase, hardware view. But sometimes we have system operations views as well. But this cost effectiveness becomes a hard problem, one that is not easily solved and probably never will be. How do you determine when something is cost effective? It's pretty hard in the information security world to prove that you've done a good job, because you've done a good job if nobody has made it in, but maybe nobody's made it into your system because nobody's interested, and you've got a lot of vulnerabilities. So how do you measure this? What's the probability of breach? What's the cost of data revelation? So if my data gets out, what kind of cost does that have to my organization or to my customer's organization? How much is it going to cost him to recreate data that is destroyed? How much did it cost him to develop that intellectual property that he's now lost? That becomes part of the cost factor here. If it's privacy data, or in the case of like TJ Maxx, it's credit card data, they've got a lot of legal costs that they incur because of that breach. And some of those may be catastrophic costs if the shareholders decide to sue because they have not performed the due diligence necessary to operate a system. And you balance all that sort of thing with the cost of protection, the impact of performance, and so on. And again, know the acceptable risk rather than striving for mitigating all possible risk to zero. One of the concepts that had a lot of input years ago, and I guess we talk about it less now than we used to, is the trusted computing base. That's the components of the system that we know something about. We know how much we can trust we can place in them. And these are the components in the system where we want to do the most valuable work. So if I've got a distributed system and part of it operates in the cloud, part of it operates privately, what do I want to do in the cloud and what do I want to do where my trusted computing base is unknown versus what I want to do locally where I have some control over the trusted computing base. Do I need to, in order to protect the things that I'm trying to protect, do I need to actually develop something myself, or can I go out and find it? Or can I adapt something that is already made to do the job for me? And then how much assurance do I have to put in things? So the next phase in the system engineering lifecycle is implementation and test. So here's where we start doing things like testing for functionality. So we have to generate our test plans, our test processes, we have to conduct the tests, we actually have to figure out how we're going to conduct them and if the conduct of the test is sufficient to get me an answer that I'm looking for. How do I report the discrepancies that I've found? And then how are those discrepancies fixed? So who fixes them? How does it get back into the system engineers, the software engineers, hardware engineers, to get a workable solution back into test? And then you may have accreditation testing, which is kind of the opposite of functionality testing. Functionality testing, you test something to prove that it does what it's supposed to do. In accreditation testing and security testing, you actually are trying to devise tests to prove that it doesn't do what it isn't supposed to do. And if I have a system that's got 14 million lines of code, how long do you think it's going to take me to exhaustively test that system? Will I ever get done? No. So my test procedures and my test plans have to, and my test engineers have to understand what's important and how do I test to make sure that what's important is tested. And then it goes back to the vulnerability and threat analysis that I did earlier. I've identified the vectors by which an adversary may attack my system. Now I need to test to make sure that I've blocked those vectors in some effective fashion. Have I made it so expensive for him to be able to breach my system that he's going to go to somebody else? He's going to spend his time on somebody else and not me. It's the same kind of thing as running from a bear. If you're faster than your companion, you've got it made. This is the stage in which it gets the most attention from the certification and accreditation activities and the formal security evaluation. But you can see from the design here that this extends all the way back into the beginning of the phase. So here is the culmination of the work that you started in the security requirements phase of your life cycle. You will do another risk and vulnerability assessment at this point. Now what you're looking for is, were the risks and vulnerabilities that you tested for or that you looked for before fixed, but are there new ones? So a year ago you started your system development on Ubuntu 13. And today, Ubuntu is up to 16, and they've done a number of patches. Is your residual risk and vulnerability assessment the same as it was under a previous version? You know, so if you're all Linux and you're all doing it as a Linux, your entire project is Linux, that's one set of calculations. If your project is Windows, you've got another set of calculations that you have to do. And if it's got a mixture of things in there, then you've got yet another one to do. So you've taken a look at what you knew was your residual risk before, and you have to determine, has my residual risk changed? And if it has, what do we have to do to get it back to that same level of acceptable risk to the designated approving authority who's going to sign off on the system as being operable? Helps if I hit the right key. Along that same line of the certification accreditation, if I can get my accreditor and my certifier involved early on, then I can train him in thinking the way that I'm thinking, and I can help I can understand what his thinking is. But don't rely on that making your job easier, because that CNA authority or designated approving authority will have changed 3 times by the time you get from system design to the time you get to this particular point, and you will have had to train up 3 other people or 2 other people. And documentation, documentation, documentation. More documentation. There's a number of levels of certification accreditation that you can go through. The DoD and the intelligence community in the United States have started to get together and said DICAP, DITSCAP, and some of the other common criteria and Orange Book certifications that we've had to go through in the past is too many. The Office of the Director of National Intelligence has said, get together, we're going to have one certification and accreditation framework. And of course everybody said, nah, that ain't going to work. And so now we've got the overall document, and now we're going to have implementations specific to particular customers. But at least there is now the hope that it'd be more uniform when working towards the certification for the government. Commercial world, there are probably as many ways to certify an accredited system to get it online as there are customers. But one of the certifications, I'll put quotes around that you may see is something called a SAS 70. And this is an accounting standard document that says that somebody has reviewed this and they believe it to be, they've reviewed your documentation and your processes and how you got to where you are, and they believe that to be good and true. Doesn't necessarily mean that it'll operate as you say it'll operate. And now the final phase, which is the transition to operations, and then the operations and maintenance phase. So when you're designing in the early part of the system engineering lifecycle, you have to consider how the system is going to be used. Who's going to use it? The skill level of the operators, the skill level of the managers, the skill level of other kinds of users. Is it an internet-facing system? Then you have to assume a skill level of near zero. If the great public is going to be, if your grandma is going to be the primary user of this system. If it's a video game, there's probably a different skill level. Now we start exercising things called disaster recovery and business continuity of operations plans. So if you've designed it well, then you know you've got a backup system, and you know the backup system will work, and now you get to prove it. During operations and maintenance, some organizations kind of give just a lip service and a quick passing kiss to the disaster recovery plan, and then something happens and they're essentially out of business for a period of time while their system recovers. We can think of this past winter on the East Coast. The amount of snow on top of some buildings caused leaks, which caused systems to fail. And if there were no backup plans, if there were no continuity of operations facilities, then some companies may not have been able to, or were not able to, operate for a period of days while snow melted and cities cleared the streets. We need to figure out how we're going to monitor the performance of the system, and in our case, particularly the security performance. So a firewall that we install today is not going to work as a firewall that we install tomorrow. In fact, maybe we don't even need a firewall tomorrow. Maybe we need something else. Plus, we have to pay attention to what the new risks are. So we just upgraded from Windows Vista to Windows 7 on all our user interfaces. What are the new risks to that? How do we resolve those? And then, how do I get rid of the system? Okay. Terabytes of data. And I want to move all this data off this one platform to another platform. What do I do with the hard drives? Do I want my hard drive to show up on eBay with all my privacy information or all my design information available for whoever bought it to find it? So we talked about these. So in the process of this system engineering lifecycle, you're going to have lots of things in your toolbox. And what you select to put in your toolbox is going to depend on a number of things. Who you're working for, what your job is, what you're comfortable with. But consider tools for the design and architecture. Consider your tools that you're going to be doing for risk management, vulnerability analysis. What kind of tools are you going to be using to monitor your systems? And I'm not making any recommendations. So, you as a system security engineer have a role in all aspects of the lifecycle process. I hope I've proven that to you. You all already are believers in system security engineering as being important, and we now see how we can enable a number of functions all through the systems development. We hope we have well-defined processes. We hope we are continuously improving those processes. We work to continuously improve those processes. Requirements, engineering, design, architecture all have approaches that we address throughout the system lifecycle. And at the end, before we can get things going, we have to figure out that we've actually considered all of the aspects of the requirements and the operations, disposal, disaster recovery, so on and so forth, before the system is turned on. So are there any questions? Yes?
When you're talking about functionality testing and accreditation, the aspect of accreditation that you're talking about, how do you verify a certain application that you develop? Is it based on a security level, or is it based on, you know, the qualitative analysis of the unwanted functionality or the quantitative analysis of the unwanted functionality? I mean, how do you evaluate that the software is safe enough so that you can implement it in the production environment?
If you've developed it yourself, you have access to the source code. If you have access to the source code, or you can require access to the source code, you can start doing you can use some source code analysis tools to determine that there's not unwanted functionality in there. But Microsoft is not going to give you the source code for Office. Apache's you are going to be able to get the source code for the firewall, like the Tomcat firewall or something like that. So you can do an analysis of that. You can also install it and beat it to death, and to see what happens when you stress it, or when you exercise the attack vectors that you expect that your adversary can use to get to your system. So you can do those in small bits and pieces, and then you can aggregate it together. If you've got enough money and time, you can then test a larger system. Source code analysis is probably the best but hardest piece to do. You can also rely on other people's testing. So we have something in the United States called the common, or in the Western world called common criteria. So Germany, England, France, United States, Italy are all signatories to the common criteria. And then there's levels of common criteria. There's level 1 through level 6. And level 1 security targets are pretty basic. Level 6, there's been a formal analysis of the product for covert channels, and so there's quite a spread between these two things. But in order for it to be evaluated at common criteria, somebody has written a security target. They say, this is the security aspects of this system, this is what it's supposed to do, this is the target that we've gone, and then there's a performance evaluation by some outside organization that has evaluated whether this product meets its target. And if you had an EAL4 evaluation performed on a particular product, you've written the security target, some common criteria lab evaluation facility is going to certify that you met your target. So somebody then takes your product and says, oh, I want to use this widget that was developed here. They're going to go look at the security target and say, oh, that's not the same security target I had. Guess I'm going to have to go look elsewhere. Or they're going to look at it and say, close enough. Or they're not even going to look at it and just say, this was the AL4, we're going to use that. But the good engineer will look at the target and say, yes, it met it, or no, it didn't, and if it didn't, then they may want to take it through an evaluation to meet their target. Did that answer your question? Any other? Dan.
Steve. That second to the last bullet, I think, of course, is very interesting. I was wondering, in your experiences, perhaps, if you can comment on. Oh, sorry. If you can comment on whether the system security issues come in as constraints or parts of the objective function, and are they sort of, does the program manager or someone else who's worried more about performance try to avoid them at all costs until forced to deal with them?
Yes.
Yes.
Yeah, I have seen the last, and actually that probably was more common a few years ago for program managers to just kind of wave their hand and say, we'll solve that problem when we come to it. Because of the heightened awareness of cybersecurity issues, and because of the increase in the threat and the vectors by which that threat can be realized, people are realizing that they have to identify and mitigate some of these risks earlier in a program. There's been some spectacular failures, as you're well aware. The trade-off that you make is, I mean, it's far easier to write that sentence than it is to execute it. I could, as a security architect, I probably could take over the entire budget of a project and just solve the security problem and not the basic problem that the solution is trying to solve. So I have to, as an architect, I have to perform some of these trade-offs, and I have to understand what the cost of my solution is in dollars and in performance and in a number of other factors, and how it's going to affect the schedule. Now, I'm a believer that if I'm brought on to a program early enough, I can actually facilitate the meeting of schedule and cost bogeys for a particular program. If you wait to bring me in until the design phase, it's too late. I'm going to make your life misery if I'm given enough authority to do so.
Our recording ability stops here in just a moment, so we'll call that our last question and thank our speaker, Steve. Thank you.
Thank you.